Assalamu alaikum wa rahmatullahi wa barakatuh. This is the fourth video of Mechanical Oscillations Part 2. At the end of this video, you're going to be able to explain the free undamped oscillations of a simple pendulum. Let's remember first what we have taken in the last video. We have mentioned that in the case of a compound pendulum, Hg can be found as A into 1 minus cosine theta. The center of mass can be found as sum of mixi over the sum of the mass of the particles. The differential equation of compound pendulum is given by theta w prime plus omega 0 squared theta equals to 0. The time equation then is theta equals theta maximum sine or cosine omega 0 t plus phi. Finally, its proper pulsation was omega 0 equals to the radical mass g a over I, where the proper period was t0 equals to pi radical I over mga. First, we're going to define the simple pendulum. A simple pendulum consists of a body of a mass m taken as a particle suspended from a light and inextensible string of length L, which is fixed at its upper end. The pendulum rotates in the vertical plane around the horizontal axis of rotation, which passes through the upper end of the string at point O. Then, this pendulum performs oscillations between the two extreme positions, theta maximum and minus theta maximum, and around its equilibrium position. As we have done before in the previous videos, to study the motion of this pendulum, first we have to look for the expression of the mechanical energy, starting with defining the system. The system here is the simple pendulum and Earth. At a given instant t, the mechanical oscillation for this simple pendulum is the kinetic energy and the gravitational potential energy. What is the expression of each one of these energies? Since the system here makes a kind of rotation, so the kinetic energy is half I theta prime squared, while the gravitational potential energy is given by mghg, where the horizontal plane containing the equilibrium position is considered as the reference level of the gravitational potential energy. To find the height hg, we are going to use the following figure. At a given instant, g is above the reference by a height hg, where it is OG0, which is L, minus OH, and OH equals to L cosine theta, taking into consideration the following triangle OHG. Then OG equals to L into 1 minus cosine theta. So the gravitational potential energy can be written as mgl into 1 minus cosine theta, and finally the mechanical energy is half I theta prime squared plus mgl into 1 minus cosine theta. The second step is to find the differential equation. We used to find the differential equation in two methods. First, by mechanical energy. Second, by Newton's second law. In this video, we're going to study it only by mechanical energy, and you can use Newton's second law in order to find the differential equation. We have found that at an instant t, the mechanical energy is given as half I theta prime squared plus mgl into 1 minus cosine theta. But there is no non-conservative forces, so the mechanical energy is constant, thus its derivative is 0. We should remember that at instant t, theta prime is d theta by dt. The derivative of cosine is minus sine theta times theta prime, while if it is minus cosine theta prime, it is written as sine theta times theta prime. The derivative of theta prime is theta w prime, where the derivative of theta squared equals to 2 theta prime theta w prime. How can we use these rules in our study? Let's go back. The derivative of the mechanical energy is 0. Then the derivative of half I theta prime squared is half I into 2 theta prime theta double prime plus the derivative of mgl into 1 minus cosine theta is just mgl sine theta times theta prime. Since the derivative of mgl times 1 is 0 since it's constant. You should know and you should study it that for theta maximum, very small and less than 10 degrees, sine theta can be written as theta in radians. So the above expression can be written as 0 equals I theta prime theta double prime plus mgl theta theta prime. Take theta prime common with theta prime is not 0 and using the expression of the moment of inertia of the particle as ml squared and replacing it in the expression of the differential equation, we can get finally theta double prime plus g over L theta equals to 0, and this is the second order differential equation without a second member, theta, for the simple pendulum. Note that the simple pendulum is a special case of the compound pendulum. Remember the differential equation of the compound pendulum, which is taken in the previous video, theta double prime plus mga over I times theta equals to 0. Now in this case, instead of talking about the position G, which was away from O by a distance A in the compound pendulum, here this distance equals to L, the length of the string. And the moment of inertia of the system, which was I, we can replace it here directly by ml squared. Replace both in the expression of the differential equation, we can find finally that it is theta double prime plus g over L theta equals to 0. Now this differential equation is of the form theta double prime plus omega 0 squared theta equals to 0. Then the motion is simple harmonic and its solution is of the form theta equals to a sine omega 0 t plus phi or a cosine omega 0 t plus phi, where a omega 0, phi and phi are constants where theta maximum is always positive. The proper pulsation is omega 0, which is radical g over L. The proper period is 2 pi over omega 0 and it's 2 pi radical L over g. The proper frequency is omega 0 over 2 pi and it's 1 over 2 pi radical g over L. Let's solve this application. A simple pendulum is formed of a particle of mass m suspended from an inextensible string of negligible mass and of length L equals to 50 centimeters. The pendulum is displaced from its equilibrium position, theta equals to 0, in the vertical plane by an angle of theta 0 equals to minus 0.15 radians. At t0 equals to 0 seconds, it is released without initial velocity. At instant t, the angular abscissa is theta and the angular velocity of the pendulum is theta prime, which is d theta by dt. Neglect friction and take the horizontal plane containing the equilibrium position as a reference level of the gravitational potential energy. Write at an instant t the expression of the mechanical energy of the system pendulum Earth as a function of theta, theta prime, m, L, and g. We start with the expression of the mechanical energy that we know. The mechanical energy is the kinetic plus the gravitational potential energy. The kinetic is half I theta prime squared, while the potential is mg hg. With hg equals to L minus L cosine theta, we can write it as L into 1 minus cosine theta. We can replace it also in the mechanical energy as half I theta prime squared plus mg L into 1 minus cosine theta. But you should know and you should study it that for theta very small and less than 10 degrees, cosine theta can be written as 1 minus theta squared over 2. And we can replace I by its expression ml squared for a particle. Finally, the mechanical energy is half ml squared theta prime squared plus half mgl theta squared. The second part, determine the differential equation that governs the motion of the pendulum by theta. We know that the non-conservative force doesn't exist, so mechanical energy is constant and its derivative is 0. Now, if we make the derivative, we can write it as half ml squared into 2 theta prime theta double prime plus half mgl into 2 theta theta prime. Dividing by ml2 and half, we can write it as L theta prime theta double prime plus G theta theta prime equals to 0. With theta prime is not 0, we get finally the second order differential equation. The last part, the solution of the differential equation is given by 0.15 sine to radical 5 t minus pi over 2. Calculate the angular velocity of S as it passes through the equilibrium position for the first time. Directly you will think of finding the expression of the angular velocity, and it's not wrong. So theta prime equals to 0.67 cosine 2 radical 5t minus pi over 2. But at equilibrium position means theta equals to 0. So theta equals 0.15 sine into 2 radical 5t minus pi over 2 equals to 0. And that means sine 2 radical 5t minus pi over 2 is the 0 part. How can this information help us? We know that sine square alpha plus cosine square alpha equals to 1. That means cosine alpha can be written as radical 1 minus sine squared alpha. So if we have sine of an angle 0, then cosine alpha here is 1. We can say then cosine of 2 radical 5t minus pi over 2 equals to either plus or minus 1. Then theta prime is plus or minus 0.67 times 1. To choose which one is correct, the positive or the negative, we go back to the question that says they want us to find the angular velocity when the pendulum passes through the equilibrium position for the first time. When it starts from the negative side and moves to the positive, then theta prime should be positive. And here we say theta prime is plus 0.67 radians per second. At the end, you can memorize these main ideas that are mentioned in this video. But all in all, we can make a comparison between the differential equation of the 4 pendulums that we have mentioned before in the videos: elastic pendulum, torsion pendulum, compound, and the simple. You can observe that each one has its own angular frequency and period depending on the characteristics of the oscillator, either K and M for elastic pendulum, C and I for the torsion, M, G, A and I for the compound pendulum, and finally just G and L for the simple pendulum. Another analogy is between translation and rotation. We can find that the dipsessa differs between translation and rotation and all other physical quantities. This is the end of part 4. Thank you for watching.